Hello everyone, this is the solution video for homework 2. Now, we had the same system as we had in homework 1, and we also had the same specifications, namely 10 seconds of settling time and 10% overshoot. And the tasks were as follows. We were asked to define all the PID controllers that regulate the heat as desired, and we are going to use the algebraic method. By the way, our controller will be parametric. So let's start with the PID controller. I have already prepared the necessary definitions here. We have the transfer function. We convert it into a symbolic expression. We have the overshoot settling time, the zeta and omega n values, and that's basically it. Now, when we want to define all the PID controllers that kind of satisfy these specifications, what we mean by that is that two poles of the whole closed loop are already specified. Now, since the PID controller has three parameters, let's also define them by the way, KD, KP, and KI, which are real coefficients, we basically use two coefficients to assign two poles, or one set of complex conjugate poles, and the remaining one will be basically the free variable that we can use. If we have a certain polynomial of a certain order, we need, if the order is, let's say, n, let's start with n equals 3. If we have a polynomial that looks like a2s squared, a1s plus a0, we need controller parameters for each coefficient in order to change all the poles freely. If we want to, for example, assign a set of poles, like -1, -2, -3, for example, for this polynomial, then we need access to a2. We need to influence this coefficient somehow. Let's call it k2. We need to influence a1 plus k1, and we also need to influence the constant coefficient here, so that we get basically all the poles that we want. If we are missing certain coefficients or certain influence to coefficients, namely this one here, that would translate into the following. We cannot freely assign all the poles of this polynomial. We can only partially assign the poles here. And when we drop down to just only one coefficient, then you already know what's going on here. We will have the root locus in terms of k0, and we can see how we can move basically the poles in this case. So if you have an nth order polynomial and you want to assign n poles, then you need n coefficients. And for the PID controller, we have three parameters. Due to its nature, since we define the PID controller KD times S squared plus KP times S plus KI, we can already see that this is basically a second order polynomial. And since the system, in this case it has no zeros, but even if it had, if we have the system, if we take the closed loop, it will appear at the coefficient, at the constant coefficient, at the S term and at the S squared term in terms of influence. So what I mean by that is if you examine PCS, which we will do in a minute, you can see that there are coefficients in S squared, S, and Ki. Of course, in this case, we will multiply the denominator of the open loop system with S, so they will be shifted, sort of, and we will add this polynomial to it due to the formula that looks like this. Fs times Cs, 1 plus Fs times Cs. If we decompose it into the numerator and denominator, So let's take PCS, S, all, and also PCS in order to see what's really happening here. So you can see that the constant term is affected by Ki, the S term is affected by Kp, and the S squared term is affected by Kd. But then we have two more coefficients which don't have unknowns or controller parameters in it, which means that we have 5 set of poles. It's a fifth order system. We cannot change all of the poles as we wish. We can just freely place 3 poles of this polynomial. And what we are going to do here is we are going to choose just 2 poles, or a set of complex conjugate poles, and we will choose just 1 free parameter in this case. So let's actually do that. Since we have a fifth order polynomial, characteristic polynomial, let's define A, B, C, I guess. Let's call them real. And define the residual polynomial here, A times S squared plus B times S plus C. And the problem is, as usual, get the coefficients of PCS and equate that to the coefficients of PDS times PES, all the coefficients. Of course, we didn't define what PES is. Let's quickly do that. Here, PDS equals S squared plus 2 times zeta times omega n times S plus omega n squared. So, of course, we need to free parameters. So, when we are solving it, we are going to say, okay, this is the problem. These are the parameters that I'm interested in. Let's have KD, KI, A, B, and C. So KP is my free parameter in this case. And let's see what the result is going to be. There we go. Now we have sol.A, sol.B, sol.C. And we can already see that, for example, sol.A is positive, and then we have sol.B, which is also positive, and we have sol.C, which is depending on Kp, but the stability of this residue polynomial will depend on this, and if we have at least A and B positive, it seems like we're on a good way. Now, since we know what KD looks like and KI look like, what we can do is we can do the following. Let's say we want to define all the controllers, all the PID controllers. We can just substitute or even go ahead and write it down ourselves. Sol.kd times S squared plus sol.kp. Actually, kp is our free parameter, so kp times s plus sol.ki, the whole thing divided by s should be our controller. So let's see. Now this doesn't look pretty, so let's use VPA, comma 4. And maybe we can also use pretty. There we go. 1.25 kp minus 6.651 s squared plus kps plus 0.5723 kp plus 1011 divided by s. So these are all the PID controllers that have the complex conjugate pole, depending on or calculated by zeta and omega n, as a common complex conjugate pair of roots. So basically we have assigned the poles, but we don't know what the residue poles look like, so they will be moving, but all that is going to happen is we will have 2 poles at the exact same spot, but the other ones will move. So basically, this is a family of old PID controllers. Now, if we are going to take stability into the game, if we want to look for stability, for example, what we can do is we can go a step further and use sol.a times s squared plus sol.b times s plus sol.c times sol.c, and maybe repeat this step. Maybe pretty is not really important. Just use VPA es2. So this is basically the polynomial that we end up in. And what we can do is we can, of course, look for the root table of this. Just 1, 8.2, 1798, and then the other stuff. But I can actually see that the positivity of this should give us a certain bound. But if we want to be even, if we want to take it even a step further, if we want to look to it in a more detailed version, what we can do is we can also kind of convert this into something that we already know. So yeah, we can numerically actually attack this problem. So maybe we can go ahead and define omega, a real value here, and just substitute ps to s1I times omega. Then we would then solve for the real part of p omega should be 0. Also the imaginary part should be equal to 0. And that should give us another solution. Of course, if I use it sol, let's call it sol w here to distinguish it. I don't want to lose this solution here. So as usual, we have three values here. Sol.kp, if we convert it into double, it is called sol w.kp. So we can see that it is negative 1.76 and 116.2 approximately. The omega values here are, of course, not really that relevant. We are not interested in the values, but we can see what's really going on. One of them is negative, one of them that should be eliminated, but we get a zero crossing, which is the origin. We get a certain frequency, 4.2, which gives us a j omega crossing. So based on this, what we can say is, we can say that all the controllers, when we use this here, should be in the interval 1.767 kp 116.196. So if we are talking about, and I'm going to erase this part here because it's not really that important. We have already worked it out. So if we are talking about all stabilizing controllers that have a common complex conjugate root with these theta and omega n values, then we should also provide this interval here. If we are not really interested in stability, then we can just give this expression here. But of course, this without stability doesn't really make sense, so it would be a good idea to provide the interval kp here. So, of course, this is still not enough. If you think about it, we just have a stability interval here. This could mean that one of the residue poles can be in the dominant region. So ideally, we don't want this to happen. So if we look at the question, it seems like all the PID controllers that regulate the heat as desired, that doesn't translate into just the controller given here. It should also consider the dominance of the two poles that we are given here. So maybe Kp needs a better interval to at least push it away from the dominant region. So technically speaking, this wouldn't be enough. But of course, in terms of the homework, I'm just looking for this here. And maybe if you have provided it the stability interval. But the stability interval doesn't guarantee us that we will get 10% overshoot and 10 seconds of settling time for the system. Or not all the PID controllers in this interval are do have this property. So do not satisfy actually the requirements here. So ideally, we would shrink this interval into so that we have the residue poles out of the dominant region. So we'll come back to this later. But for now, we can see these are the PID controllers, and this is the interval. So now the next question here is about the maximum dominance factor of the residue polynomial. And then we are going to repeat it for the zeros and overall. So what this means is the following. We know already parametrically what KD, KP, and KI look like, depending on KP. Maybe you have chosen something else, but it's basically the same story. Now, if they are depending on this KP parameter, I can examine all the possible set of roots of the residue polynomial, which looks basically like this. So let me run it again. So I can see what the polynomial looks like. I would like to see how they move in terms of roots when I change KP. It is depending on KP, and I'd like to see the movement of the poles. And furthermore, I'd like to also see what the dominance is, because these three poles of this third order polynomial, the roots of this, are the residue poles. And I'm interested in pushing them away as far as possible to the left from the dominant region. And I already know what the real value of my dominant poles are. So how can I convert this into graphical data and also maybe numerical data in terms of a table maybe to see what's really going on? So we already have calculated the vector here. So I can do something like kpvec here and use maybe linspace, maybe something else. Let's use linspace. Minus 1.7, maybe 117, and maybe 100 points. So what I can do now is I can look for each kp value, plug it into PES2, the residue polynomial here, and then look for the roots. Once I have done that, I need to kind of see which root I'm interested in. Maybe not the roots directly, but I could do something else. Let's see. So let's open up our for loop here from 1 to length kpvec here. So basically this is part B. So this was part A. There we go. Now, kpval is kpvec I, and then now, so let's call it temp. Let's substitute PS2 the kp value. Now I'm interested in the roots, so let's call it poles, double roots coefs of temp s and all poles. So for the sake of simplicity, let me just iterate to 2, not the whole range. So now we have the poles here, and I can see that there is one approximately at the origin, which is not a good idea, and which is what I was talking about. It is in the dominant region because of the stability interval, so this is not really a good value or a value that we're interested in, because it will be at the stability bound. This one is also not the interval that we are interested in, because this will also be a j omega crossing, and it will still be around the dominant region, even more dominant than the supposed poles in this case. So it should be in the middle somewhere. So we'll find out. Now, what about the dominance factor? So I'm interested in the dominance factor. Well, let's call it ME, zeros size KPVAC. And the way that we should calculate this dominance factor, E stands for residue, because PE, is the following. We have the poles. We are actually not interested in the poles because that the poles can be complex values. We are interested in their real values because that will define our distance on the real axis, and we are looking at the distance from the origin on the real axis. So therefore it should be a real value here. And once we have the real value, what we can do is we can get rid of the negative sign using the absolute value. If you do abs first and then real after, it would make no sense at all, because if pulse is a complex value, you will take the absolute value, which is already a defined thing, which is the modulus, which is the radius from the origin, and then taking the real, because there are no complex values from the absolute value, so this will do nothing, so you will end up in absolute. It's not the same. We're interested in the real value and the absolute value of that, because this is called distance. You might also skip this absolute part, but that could give us an indication about the stability, but since I've examined the stability interval, this should not be a problem at all. So, you can use minus sign, you can use absolute, whichever you want. Now, this is still a vector, by the way. Let me show you. This is still a vector, and I'm only interested in just one of them. And which one am I interested in? Well, if you think about the poles, let me just quickly demonstrate to you. Let's have some poles on the left-hand side. Let's have the dominant pole pair here. Let's put in a star here. So this is the dominant pole. And let's have the origin. Now, I'm interested in the closest one, the closest to the origin, because it doesn't make sense if I have these two poles, because this one is the closest one and it will have effect on the dominant pole pair. So I should look for the minimum distance, or the minimum one, of the residue poles, because that would be the closest one. So if I take min, and you will see in this example it makes sense because I'm interested in 0.0047 because it is in the dominant region and it is in fact on top of the origin itself. I'm not interested in 4 because it's further away, but I have still something in the dominant region which violates the fact that we are interested in dominant pole assignment here. So I'm looking for the minimum. As you can see now, it is becoming better and better. So let us store this. Well, this is still not the dominance factor, but this is the pole that we're interested in and its distance from the origin. What I can do basically is I can maybe go ahead and define something called sigma. So let's call this sigma zeta times omega n, which can be used for the settling time calculation here. So I'm going to use divided by sigma in order to get the ratio that I'm interested in. So now it looks like this. What is sigma on its own? It's 0.4. So let's calculate this. Let's assign it to ME, and we should be good to go. Now let me open it up back again, like this. So let us create a figure. And let me plot KP versus ME line width of 2. X label would be KP, Y label would be dominance factor M, and the title would also be dominance factor. So, takes quite some time to calculate it for some reason. Finally, now we can see that the dominance factor drops down to 0 here when we have the negative bound on stability, and then we have also again 0 if we look at the upper bound of the stability interval, and between these we can see that there will be a maximum point. Now, in terms of dominance factor maximization, which is our aim, because it would be nice to have them as far away as possible, the residue poles, because then it would practically convert it into a second order transfer function because they are all far away, and our settling time and overshoot formulas will be valid, so everything would be okay. It would work. Now, it would seem like this will be our point of interest. Now, in the task here, we can also see that we are looking for the zero polynomial 2 and then overall. So what I'm going to do is I'm going to assign this a display name here. Display name, call it residue, and I will have something called MZ, which will be representing basically the zeros here. We will only have 2 zeros, so it will not be that bad. So let's again have this here, but instead of having PES, we can use PZS, or we can just directly use the polynomial itself. I guess in PZS we didn't really define it, so we should still do it. So sol.kd times s squared plus kp times s plus sol.ki. We will substitute kp val into kp. In this polynomial, this will be our zero polynomial. Now we will look for, let's call it zeros. We are looking for the zeros. The calculation is basically the same because we're still interested in the same thing. It doesn't really matter if it's a pole or a zero, but we're looking for the real value of the zeros, take the minimum of the absolute value, or you can also use the negative sign, and then divide it into sigma, and we will have mz. So, yeah, it takes some time. I don't know why. Yeah. Why do we see an answer here? Oh, because of PS2, I guess. Yeah, nice. So, if we look close to this one here, we can also see that the zeros have kind of the same root here. At some point, we cannot push them away because here we have a constant dominance factor here. So I can conclude from this graphic here that these zeros here are probably complex conjugate pairs because the real value does not change, but the imaginary part of the zeros will grow and grow and grow, I guess. And we can see that again it drops down to 0, it's in the dominant region. Now, if we are realistic and if we are okay with some deviation in the specifications, it seems like around 3 times the dominant region, the dominance factor being around 3, is kind of the region that we are interested in. So it looks like this here, this interval here, could be the interval that we are interested in. So you can see that the KP interval in terms of zeros is quite tight. It's around 8, 7 point something, 8 point something. It's quite narrow. If it were for the poles, we would be okay with this whole interval here. So like 6 or 7 here, and then it would be 17 something here. So it would be a much larger interval. So we can see that this is a problem on its own because we have a set of poles to push away and a set of zeros to push away for a PID controller. And we, of course, have to push them both as far as possible to the left. So what can we do in this case? So we can combine these two graphics here, actually, and the operator to combine them would be the minimum here. Because again, we need the closest one. So we will take the minimum of both graphs and we will create an overall dominance factor graphic here. So which one is minimum, that one will basically become the actual dominance factor. In this case, for example, it doesn't matter if the poles are far away. If there's a 0 in the dominant region, that 0 will define the overall dominance factor. In this case, again, the zeros are quite dominant compared to the poles. And once we reach this point, for example, here, the zeros stop moving, but the poles get into the dominant region. Now on this branch, the poles will be dominant here. So we will take the minimum of both graphics and look at the result. So let's call this, by the way, I didn't create MZ. So let's create M. And M will be calculated by the minimum of MEI, comma MZI. I should have dropped down the samples, but yeah, we have to wait a little bit. Now I will see the overall dominance factor, but I'm also going to talk about something else. I might also want to see them in action. So you can see now that on this branch the poles are dominant because they are the minimum, and then the zeros become the dominant in this region here. And in this region, again, the poles are minimum. So we're on the minimum path here. So the maximum of this will give us the ideal solution. It is going to be this tip here. So let's basically calculate that. Value, comma, index. The maximum of M. I'm interested in which KP value it is actually. So KP val would be then KP vec, the index here. At that point, what I can do is I can just calculate the remaining PID parameters here. So double subs sol.kd instead of KP, use KP val. I didn't store everything somewhere. You could do that, but it's not really important, and I did it didn't do it. So since we're on our way, let's define our PID controller, because we've actually accomplished the design here. KD val, KP val, KI val, and then the closed loop using feedback. Let me remind you of something. If you are going to use fs times gs and then 1 plus fs times gs, which is possible, you have to use min_real here in order to get rid of the pole zero cancellations. So let me, yeah, I don't really want to drop that down too. So yeah, let's run it. If you don't call min_real, and if you call pzmap, for instance, you will still see the pole zero cancellations on the plot, on the graphic, which is not quite nice, because they don't actually exist, because they are cancellations and you should get rid of them. If you are purposely canceling out something, that is another story. But if you're just using the feedback connection and try to calculate it, then there's no pole zero cancellation there. So I misspelled something here. KP vec. There we go. So TS. And if you run ZBK TS, even in this case, we still see s plus 1 squared and then s plus 1 squared. So this shouldn't happen. And if you're not okay with this, as far as I remember, there's also a certain way of eliminating them. So it's still, now it works if you provide that. But I discourage you to do that, because, well, it complicates things. And yeah, instead of doing this, just do it the old-fashioned way. Use feedback, fs times cs. It will get rid of the unnecessary stuff here. So, I'm going to create another figure. I want to look at the step response. Call it step response. So what we can do is we can actually give the title later, maybe even do something like subplot. First one of this. So let's have y comma t step ts info equals step info ts, and then plot t comma y. And then maybe step response, whereas the information is going to be displayed. So string info dot settling time, and then plus overshoot info string info overshoot. I guess we should divide by 100, but yeah, maybe let's put in percentage here. Okay, this should be it. Now, in terms of this, I just want to get the poles and zeros, pzmap, and then ts, plot them, real of poles, imaginary of poles, use x, maybe something like this. And then zeros. Circles. And last but not least, let's also look for maybe when we are at it, let me just calculate omega d here. Square root of 1 minus zeta squared times omega n. So I can just directly plot it using sigma and omega d minus sigma. So minus sigma and minus sigma, then omega d and minus omega d, kx line width 2. Now this is basically our design point, or the poles that we want to see. I'm just showing them extra. It's not really that important. Let's see. So, yeah, let's wait a little bit more. Oh, we didn't change. Yeah, nice. Now, at this point, we're actually done with the second task, but I want to talk about something else, just to remind you of something. Now we can see it has 8.79 settling time, and we could call it 10% overshoot, which is quite nice. But then again, we can see that our dominance factor here, let's just see it a little bit, is not that good at all, because this is the best that we got here, but you can see that the set of zeros and poles are quite close to our design point here, but this is the best PID controller that we can get because of the dominance factor here. It is roughly 0.4, and 3 times 0.4 gives us 1.2 as far as I remember, and this is basically 1.2. It would of course be working better if we had 4 or 5 times dominance, but yeah, that's not possible with a PID controller with these specifications for this specific system. But we can examine the system in terms of dominance factor, because that is all that matters for dominant pole assignments. Now, keep in mind that what we're trying to do is we're trying to model a high order system like a second order system in order to be able to define the settling time and overshoot of that system. We don't have the tools, the necessary tools for high order systems to predict their settling time, overshoot, etc. That's what we are trying to do here. And the only tool that we got is dominant pole placement, which means that choose 2 poles according to the second order dynamics, push everything away, and the dominance factor here shows us how well our solution is going to work. And this is the best that we can get here. We can actually see something more about the system and examine it using something else. Here we kind of used the tabulation methods because we calculated basically the dominance factor here numerically. But what we can do is we can also use something else. We have already a tool for it, because if you look close here, we have PES in terms of KP. We also have PZS, the zero polynomial, in terms of KP. One parameter and a polynomial, an unknown parameter and a polynomial, gives us root locus. So we can also plot the root locus for this system. So let's see. That's dominance factor. Maybe I can squish it in here. So subplot, let's have 1 by 3, and the first one is this here. So I'm going to plot the root locuses here. J omega residue locus, let's call it that. We don't need the legend at all. So, how can we determine or the root locus, or how can we plot the root locus based on a polynomial that is symbolic and has an unknown controller parameter? So in PS2, we have this. What I'm going to do is, if we use VPA, we get this here. What I'm going to do is I'm going to do the following. If this is equal to 0, I can rearrange it so that I get a 1 plus k times gs formula here. 1 plus k times gs equals 0. This is called the root locus equation. You should be familiar with this. And if you can convert any polynomial into this notation where gs is a transfer function, k is the unknown, then you can plot the root locus of gs and it will correspond to the root locus of this polynomial, where you can determine the k, the interval, etc., etc. Or observe the movement of the poles of this polynomial versus the change in k. So how can we do this? Well, I have to divide into a specific polynomial in order to get this notation here. And for that, what I'm going to do is I need to rearrange the polynomial in terms of the unknown parameter. The ones that are not unknown should be on the left here. So actually, let me show you something. If we assume that this is ns divided by ds, and if you multiply with ds, you will get ds plus k times ns. So if you look at this polynomial, the ones without k are actually the denominator, belong to the denominator polynomial. So this one, and the constant term 2.2 belong to ds, and 1.25 belongs to ns, and k is kp. So then I can write down ns divided by ds, so which is 1.25 divided by the whole remaining polynomial, and that gives me the equivalent transfer function, or the transfer function that I'm going to use to plot the root locus of this. So, how can I do this programmatically? Well, I can use coefs, and I can use PS2, which is the polynomial of interest, but then, instead of s, I'm going to give it the controller parameter, or the unknown parameter in the polynomial, which is going to be kp. And of course, I'm going to use all because that is the necessity of using coefs. And once I do this, it will give me basically two terms. One that includes kp, and the other one that doesn't include kp here. Now, I know that coef1 would be the ones with kp, and so basically this has kp in it. Coef2 will have no kp at all. Now, let's actually see this. Let me show you that. So coef1 is 1.25 times kp, and coef2 is the whole remaining thing here. And together they build up the PS2 here. So you can see 5 times kp divided by 4, so 5, 4. Remember that it will not give you kp because it is the coefficient of kp. Now the thing that is left here is that I need to look for the coefs of the given polynomial s comma all, so I will get the necessary coefficients. Since I'm at it, I'm going to convert everything into double, because it should be double if they are just polynomials. Now you can see I have this nice transfer function. Actually, I'm almost about to have it. This is the numerator, 1.25 times kp, and this is basically the denominator that can be verified from here. So now I can say GES, something like that, is TF, this, which is the numerator vector, comma this, which is the denominator vector, should give me the corresponding transfer function. And it is this one here. So if you basically write down one plus kp times this equals 0 and multiply it with this, you will go back to your original polynomial. Now, I'm going to plot the root locus of this, and I'm going to skip the negative part because that's not really interesting. And I'm going to repeat this for the 0. Instead of using this, I'm going to use sol.kd times s squared plus sol. It was kp on its own, sol.ki, kp times s actually. So, the same procedure, but I'm just going to change the naming convention. That's all. Because both polynomials, the residual polynomial and the zero polynomial, are polynomials of s, and there's an unknown k, or the controller parameter kp. And all I'm doing is I'm separating the kp parts and the non-kp parts. I'm taking the coefficients, define one of them ns, the other one ds, and just define them using the control system toolbox using the TF object here. And I'm calling root locus because it knows how to plot the root locus of this, and I'm good to go. So let me run this whole thing again and see what the result is going to be. Hopefully. There we go. Now, these are basically my results now. Of course, this root locus part is not really that important, but I wanted to show you that we can track the changes here. Now, this is the root locus of, oh, I should have changed the title. The ordering is not correct, but yeah, it's not really that important. This one belongs to the residual poles because I can count 3 poles here. And I can see that actually my point of interest, if I want to push everything away, is going to be this point here. So if I want to maximize the dominance for the poles, I would quickly choose this point here because this is the point where all the poles are as far to the left as possible. Because other than that, it will just enter back the plane here on the right. But at this point, it is on the edge, or it's on the corner of it. Now, before that, we are on the right. After that, we are on the right. So this is basically the best I can get. And of course, it's 1.52. If it's 0.4, it seems like it is aligning with the results. But remember that I didn't actually use or choose this point here, which means that I'm way before that somewhere here, or maybe after that. I don't know. Depends on the KP value that I've chosen. And here, interestingly, it seems like, well, one of the poles comes to this, or actually the zeros, and the other one here meets it here, and they then together move like this. So I'm not sure what the KP value is here, but it seems like it should be on this point here. So let me check it. We have maximized M. Where was M? So what is the value? It's 3.06. So what's KP val that we've chosen? 7.89. 7.89. Okay. I guess if we would have chosen only based on the zeros, we would have chosen maybe this point here. But if we choose this point here, then the poles intercept, and that becomes an issue because here somewhere it's hard to click here. So let me just maximize it here. Let's try it again. So it doesn't have that much steps to it, which is not nice. Maybe we should change it. Let me take this title here after the root locus, place it after the root locus because it changes the behavior here. And since I know what kpval is, what I can do is I can just use, where is it now? So here I can just provide a vector 0.0. 2 times kpval should be enough, I guess. So, oh, I messed this up. There's t. There we go. So let's run it again. Let's see. So basically, we cannot choose it just based on one of them, one of the plots here. And the reason is that we are moving, for example, the zeros far to the left. We are messing up the poles. We are moving the poles. We are messing up the zeros. So they should be maximum together away as far as possible. So that kind of messes up the whole process here. And yeah, you can see that in this interval, we have already an issue about the zeros here. So yeah, the zoom is a little bit off. Yeah, there we go. Now we're talking here. So yeah, it's quite interesting in our case because the zeros move a bit weird here. So let me just show the GZS here. Yeah, we have is there something numerically going on here? I am not sure. GES, GZS. Sol.kds square plus kp times s plus sol.ki. Yes. If we use VPA PZS, 4, like this, now we get this. Okay. Oh, I get it now. Okay. We have KP in all the terms, so it kind of results in an interesting GZS, a transform, because there are 2 zeros and then there are 2 conjugate poles or even imaginary poles. So they start out imaginary, they end up in being imaginary. So a little bit of weirdness in terms of the zeros is going on here. So let me just move one of the so it moves on this branch, but it also moves here, and it also jumps here, which is a bit weird. So I'm trying to click here, so it moves here, and it moves here. So if I move this one here, 7.4, what was our KP val? 7.89. So 7.89. All right. So we've chosen basically this point here, this conjugate pole here, and let's also click here and look at 7.89, 5, 6, and it is around here. .89. There we go. Now this is the choice that we made. Of course, there's a little numerical stuff going on, or it is about the step size that we take, because if you look close, I have chosen 100. This is not the ideal thing. Since we know that it is approximately 10, what we can do is, in order to increase the accuracy here, we can just go ahead and drop this down to, let's say, 20. We know that we are not using the negative root locus here, so let me basically make a copy of it. So change the interval to 20, change this to 0, and then run everything back again to get a better result. Because of our numerical stuff here, you might want to just be careful. This graph will also probably change. It would look more linear because we've shrunk the interval to 0.20, so it would give us this portion here. But yeah, you can see that increasing the numerical accuracy here, you can also give 0.01 here. If you want to solve it, you will get the point there. Now it seems like we still have to, yeah, now it seems like it is on a better track. If we want to get as close as possible, we can still increase the lower bound. We can see that it will never be 20, so it's between 5 and 10 maybe. So let's have 5 and 10 here. From 5, 0.01 up to 10. So that should be basically it. But we can see that for this solution here, for the previous one of them was on the real axis and they were almost on the same value, which makes sense. We'll see now what the actual result seems to be. But at this point, in this vicinity, it doesn't really matter now because small numerical changes will always appear. So yeah, hope that MATLAB concludes this plot here. Bit slow, but yeah, you get the idea. We are in an interval of 5 and 10 for KP, and this is the best result that we can get. Hope that MATLAB finalizes it now. Yeah. Since we're using the root locus here, what we can do is we can basically, based on the root locus, end up in a fine interval, because this point is the furthest away. Here we are not seeing it anymore, but it was somewhere here, the conjunction. That was the furthest for the zeros. So use these two values, look numerically, and get the result that you are looking for. And you can see they are kind of aligned here. One of the poles is aligned with the real value of the zeros here, and it makes sense because that's the margin that we hit at that point. And you can also see that the minimum here works. This is basically the interval that we are interested in. This is the fine interval that we should check. And this is the best result that we can get for this system here. Now, we've spent too much time on question 2 actually, but question 3 is quite easy to solve. Well, the question is a very specific one. Rearrange your PID controller in order to get rid of the adverse effects of the controller zeros and maximize the dominance factor of the desired pulse. Well, it basically gives you a hint, and so I'm going to change it to 6 and maybe 8, 9. What is KP val? So I'm going to change it to 7 and 8. I know that the interval is there. There we go. Now, let's come to part C. This is a specific question. It actually asks us for the PIPD controller, because rearranging and getting rid of the adverse effects of zeros means that we can rearrange our controller structure so that we have a PI part here, and then we have an inner loop. Then there will be the system here, and then we will add the PD controller here. And then we will have an outer loop even. We can also plot it here, or if you're obsessed, you can also do something like this. Doesn't matter. So like this. There we go. Now, this is basically the structure that we're interested in, because it will give us the same PID effect, but it has its pros. Now, you can see, of course, we have negative signs here. You can see that the transfer function, let's call it TS1, would be GS divided by 1 plus PD times GS, and then we would look for the overall closed loop, which would be PI times TS1 divided by 1 plus this, basically. So you will get the closed loop here. Now, if we dive into the details, you can just use a pen and paper and prove this, but you can see actually that the closed loop here, since the PD is on the feedback loop in the inner loop, you will end up in no zero from PD in the closed loop here, because it's in the feedback loop. GS divided by 1 plus PD GS will have no zero for this specific system, because GS has no zero here, as you can see. Therefore, you will have no zero in this closed loop. You will have KD and KP parameters in your denominator. Once you complete the whole thing with another loop using the PI controller, you will get the zero of the PI controller. TS1 has no zero, and you will end up in the same characteristic polynomial in the denominator, or in the closed loop. So this is the reason why we call it rearranging, because what we're doing is we're kind of taking the PI times PD, so this PD part here, and instead of using it like this, we're just taking this part, placing it into the feedback loop here, so that we kind of get the same effect, but we don't get the zero of the PD part of our PID controller. And even better, not only did we get rid of the PD zero, we can place the zero of the PI controller wherever we want. And that kind of helps us in getting rid of all the effects of zeros, because there are no zeros at all. We will have one zero that we can place wherever we want, and the other one is vanished because it's in the feedback loop. But keep in mind that we don't have to redesign the whole PID controller, because what we can do is we can just choose the same KD and KI parameters, the dynamic parts, which are basically the derivative and the integral parts, we can take the same coefficients for them. And we also have to stick with the same Kp, the proportional part of our original PID controller, but we are going to split it into reasonable parts so that we can place our PI 0 as far as possible. So, as I talked about it earlier, you can just write down, you can just define your controllers, define FSPD like KD times S plus KP1. You define your FSPI like KPI, let's call it KPD, KPI plus KI divided by S, and then do the whole thing, calculate the whole closed loop transfer function, and then you will see that the whole closed loop will look like the following: KPI times S plus KI divided by whatever the characteristic polynomial is. Let me just take this actually. So this was s to the power of 5, 9 times s to the power of 4, 25 power of 3, power of 2 times s plus ki, 27 plus kd s squared plus 10 plus kpd plus kpi. That would be basically your denominator. So if you use the PIPD controller, you will get this closed loop transfer function. You can do the math and you'll see that this will be the result. And as you can see, we can decide on KPI, and it doesn't really matter if we have a certain KPI. If we compensate it with KPD, we can still match KPD plus KPI equals KP, the original PID parameter. So you can see KD is the original PID parameter, KI is the original one, and KP is the original one. What we do is we introduce this multi-loop structure here, and we divide the proportional part into KPD and KPI. And basically, based on the KI value, we can decide on KPI directly. Then we will push the 0 away. Once we have that KPI value, we can come up with a KPD value that will give the sum equals KP, and you will end up in KD, KP, and KI. Since the PID parameters are in the same place as they should be in the PID structure, we will get the same pole assignment here. So we will get the same closed loop poles. And we got rid of the zeros of the PID controller. We have a 0 that is placed manually, so everything should be better than it was. So, based upon this fact, let me just comment this out. I'm not going to redesign anything. All that I have to do is I'm just going to come up with KPI first, because I'm placing the 0. So all I can do here is I can divide Ki into something, and that something would be exactly this. Why? Because KPI times S plus Ki is the 0 polynomial. And if you look close to it, if I divide it by KPI here, I would get this here. And basically this would be minus Ki divided by KPI. So why do I choose Ki divided by Z instead of KPI? Because if I plug it in, it would give me S equals minus Z. And that's exactly what I'm looking for. So therefore, let's say I want to place it 10 times further away. So this would look like Ki divided by 10 times S plus Ki. And if you solve it, you will see the 0 is at -10. So once I know KPI, I know that the sum of KPD and KPI should be equal to KP. So KI val, as a matter of fact, I'm going to look for KPD, and it would be KP val minus KI val divided by that, or just direct KPI. So whatever I've chosen KPI, I'm going to choose KPD so that the sum remains the same. And that's basically it. So FPI, the controller, we have now two controllers, would look like this. It would be KPI and KI val. And then FPD would be then KD KPD, KDS plus KPD divided by 1. Now, TS1 would be feedback. And here I have GS and FPD because of this structure here. And then the actual transfer function would then be the feedback between FPI times TS1, 1 because of the outer loop here. The inner loop, then the outer loop, and we are good to go. Now, in this case, let me just show you the transfer function that I got here. What seems to be the problem? Ki val, kp val, kd val. Oh, kd val here. So let's run it again. So TS, and as you can see, ZPK TS, we have a 0 at 10, and then we have the desired polynomial here, and then the residue polynomials and nothing else. So we don't have any of that. The controller zeros, they are vanished now, they're gone because of the change of the structure here. Of course, the question is the following: if I am able to get rid of the adverse effects. So let me just comment it out. Now the problem is the following. If it pops up, I'm going to show you the problem. I have 3 poles to push away from the dominant region. I have 2 zeros to push them away. And all I did in the previous section was that I tried to push them simultaneously as good as possible away. So I tried to push them both away. But if I'm getting rid of the zeros, that means that I'm not interested in this 0 locus anymore. I'm not interested in the blue plot here anymore because they don't exist anymore. So that would mean that I can immediately change my controller parameters because of the structure, because I don't care about the zeros anymore. I could just maximize my design in terms of poles, because I can decide on the position of the 0 manually by using KPI, and I don't have any other 0. So I don't have to push the zeros anymore. I can just use the best possible solution for the most dominant poles, not the zeros, or not overall again. I can just focus on the poles. I can push away the poles, and it should give me a better result. Now I can see here that 7.76 seems to be the solution that I look for. Now let's calculate that. Now based upon this PID, not the previous one, because the previous one was not the best solution that I can get because I was caring about the zeros. Now I don't care about the zeros, so why would I use the previous one? I'm just updating my solution to push the poles even further away. And since I'm not going to have any zeros in the closed loop, this should be the solution that I'm interested in part C. So these are basically, this is going to be the result here. So let me just copy and paste it. Let's make it a figure 3, I guess. So here we are using TS, TS, all the zeros, all the poles. We should be good to go. So hopefully, yeah, there we go. Let me just click here to get the best result here. 775. What did I choose? 776. Let's use 775. Let's run it again. It almost did the job, but I just wanted to choose the actual point on the root locus. So basically, due to the residue poles, this point is the best I can get, basically. So here we can see this is the furthest point for the residue poles, and I've chosen that one here, but still the system has not the best dominance factor at all. It is approximately around, what is it now, 3.8. So ideally we would like to have a higher value for that, but at least it is around again 10 seconds and 7.6% overshoot. Now of course the overshoot changes because of the poles here, but it's still acceptable, and it is the best solution that we can get in terms of a PI-PD controller in this case. I can push the zero further away, it doesn't really matter. Let's maybe choose 20 here to push it a little bit more. But it'll not change that much because we're using the PD controller here on the feedback loop to compensate for this movement that we've done here. So that's basically it for this part here. What we're doing is we're kind of trying to deal with the zeros and poles when we're designing the PID controller. You can see we've pushed it to -20 and it didn't really affect that much the results because it is out of the dominant region. So yeah, and it is sufficient to use maybe 10 times zeta times omega n instead of that. So it would be sufficient to place it to 4 in this case because zeta times omega n is 0.4. So 10 times that would give us 4. So somewhere here would give us a result that would be sufficient here. And maybe we could also do some nice tricks here. Since we have 2 poles on top of each other, we could place it to 5.16 so that there's seemingly a pole zero cancellation, but it's not really that important at this point. So, to summarize it, we have used basically the zeta and omega n values, try to assign the dominant poles. In part A, we calculated the stability interval, and for that stability interval, we could define all the PID controllers that satisfy at least the stability condition and have 2 poles at the position that we asked for. And in part B, we tried to maximize the dominance of the zeros and the poles simultaneously, and it gave us a narrow band where we could have accomplished that, and we've chosen the best we could find in terms of dominance. By switching the structure to PIPD, what we could have done is we could have get rid of the zeros, so therefore we didn't care about the zeros. It got rid of the zeros. We just try to um, push the poles away. We improved our dominance factor quite a bit, but still it's around the same value, so it didn't make that much difference at the end. But yeah, this was basically the solution that we were looking for. Now for Q4, which is quite interesting, what we can do is we can just directly use a formula and solve it. Part D. Here in part D, we have basically Fs. We don't know what the controller structure is going to be, but we're going to use feedback and then TDS and then 1. So what is TDS? TDS is going to be omega n squared, so let me define it. Omega n squared and then 2 times zeta times omega n squared. So let me show you this part here. So Fs is basically this. This is not Fs, of course. This is basically LDS. So the loop transfer function, if we use this loop transfer function, I'm going to demonstrate you that. So feedback LDS, 1. If we use this here, was it -1? So this is TDS. Yep. In the open loop, TDS should be, I guess, -1. Let's try it here. Yeah, now, if we use LDS, if we give -1, we're basically converting TDS into open loop. So it would look like this. So we have a summation point, LDS, and a unit feedback loop here. Like this. So the closed loop is going to be equivalent to TDS. And you can use TDS divided by 1 minus TDS. If you do that, you will get basically LDS, and I've acquired LDS. So if you're not really familiar with this, you can just use the direct formula TDS divided by 1 minus TDS, and then min real the stuff here, but I'm not going to bother with that. So if this is LDS, so ideally in the loop, we should get basically LDS or ZPK. So let me show you that. So ideally we should have a pole at the origin, a pole at point 8, and a gain of 0.45 if we want to end up in the closed loop TDS that we are after. We've chosen basically the closed loop transfer function based on zeta and omega n as a second order transfer function, and that's basically it. We are inverting it, and if we divide this to GS, or if we assume that we will come up with an FS that will give us this loop transfer function here, if we multiply FS and GS, we should end up in LDS. We can see that dividing by GS should give us the controller, the model matching controller that we are looking for. So there we go. This is the controller that we should design. Now you can see that it places a pole at 5, and then we have also another pole at 2, and 2 poles, actually zeros. It places a 0 on top of 5, 2, and 2 on top of -1, and places its own poles, adds the gain, and that's basically it. If you use this controller in the closed loop, you will end up in the desired result for this case. The only problem here is that if we have a modeling error, that will cause some problems because the cancellations will mess up. Once that's done, you will just end up in weird behavior because yeah, you are relying on too many pole zero cancellations. If you think about it, the model should be better than perfect because you have too many cancellations, namely four. You are canceling four poles and zeros. They should all be on top of each other, which is not going to be the case, ideally. Yeah. So if you want to test this out, we can just go ahead and use this. Does it make sense to test this out? Yeah, not really that much, but we can still do it because here we are doing it um, mathematically. It's going to work here because yeah, it is calculated and there's no error, nothing else. So it will give us the result that we want. And in terms of dominance factor, since we've got rid of all the residue poles and zeros, there are no zeros, no residue poles, it's going to be infinity because, yeah, we have infinite pole, we have a pole at infinity, we can assume that. Therefore, we will have basically infinity for the dominance factor here. So as you can see, this is the ideal setup here. We've cancelled out everything here. We have just these two poles, and that's basically it. Is it a good controller? Well, since it's relying on the correctness of the model, it's of course not the best controller that you can come up with because, well, yeah, pole zero cancellation is not really uh, suited for most of the real world applications. But model matching controllers are also a good starting point in determining the controller structure or seeing what the result could be. And if you have an adaptive or a learning mechanism in your system that updates your model prediction, if you can predict the model, feed it to the model matching controller, that would be another story. So this is basically it. I also have a quick overview of the homework as follows. You can see if I would have documented it, of course, this is not the whole picture. I would add a little bit more detail, the step responses and stuff, but I took quick notes if it's solvable, if it's how it would look like if I would have solved it. This is basically the picture here. We have the set of equations. We solved KD in terms of KP, KI in terms of KP, and this is basically the controller that we ended up in. Of course, we could have added the stability interval, or even better, a dominant region assignment interval, but we didn't bother with that. In the second question, you can see we have the residue polynomial. We can convert it into the following equivalent transfer function, and then we have the zero polynomial. We can repeat the same for that, and then look at both of the we can look at both of the root locuses. I also have found out the interval here. It is 7.41 and 7.75 seems like the best. The dominance factor 3.55, and for the overall we got basically 3.25. When we use basically the PIPD controller, this will improve a little bit. This is the setup here. This is the root locus point that we might be interested in. This is the other point that we might be interested in to come up with a solution. This is not the whole picture. This is in this narrow interval here. You can see it kind of changes here a little bit. And this is basically the setup that I ended up in. And if we use the PIPD controller, we can see that this could be the result. And that's basically our residue pole here. And as I've already shown you, this is basically the model matching controller. And since this is relying on the system too much, this can be used in conjunction with other advanced system parts. But here, the good thing about this is, and we can analyze this, but it is out of our scope for now, using the PID controller or using the ideal PID controller that I've designed here, it can tolerate modeling errors to some extent. We can even maximize that, but that's out of our lecture for today. Hope that this was a explanation that helped you out in the solutions of the homework 2. See you in the next videos.